So, here's something that might seem a little strange to think about right before you fall asleep. But stay with me, because it's one of those ideas that starts out sounding simple and then just keeps unfolding, layer after layer, until you realize it touches everything: physics, philosophy, the nature of reality itself. And the nice thing is, you don't have to do anything right now except lie there and let your mind wander through it. We're going to talk about time travel. Not the Hollywood version, not the stuff with the glowing portals and the flux capacitors, although we'll get to why those stories exist and what they get right and wrong. No, we're going to talk about what time travel actually means, physically, mathematically, and why some of the smartest people who ever lived spent serious portions of their careers thinking about whether it's possible. And we're going to do it slowly. There's no rush. If you drift off somewhere in the middle, that's perfectly fine. The ideas will still be here, turning gently, and you might even dream about them. Let's start with something that seems almost too obvious to say, but it's actually the key to everything else. You are already traveling through time. Right now. You're doing it at a rate of 1 second per second, which sounds like a joke. But think about what that means for a moment. You exist in this present instant, and then that instant is gone, and you're in the next one. You can't stop it. You can't go backward. You're being carried forward through time the way a leaf is carried downstream, and you didn't ask for it, and you can't opt out. That's the baseline. That's what time does to all of us. And for most of human history, people assumed that was the whole story. Time flows. It flows at the same rate for everyone, everywhere, always. It's like a river with a perfectly constant current, and every clock in the universe ticks at the same speed. And that's just how things are. And honestly, that's a completely reasonable thing to believe. It matches your everyday experience perfectly. Your watch and your friend's watch agree. Noon happens at noon. A year takes a year. There's nothing in your daily life that would ever make you question whether time might behave differently under different circumstances. And for thousands of years, nobody did question it. Not seriously. Not in a way that led anywhere productive. The ancient Greeks thought about time, sure. Aristotle wrote about it. He connected time to change and motion. He said time is the measure of change, which is actually a pretty deep insight if you sit with it. If nothing in the universe ever changed, would time even exist? Would it mean anything? That's a question philosophers still argue about, by the way. But Aristotle, brilliant as he was, didn't have the mathematical tools to push the idea further. He could observe that time seemed to flow uniformly, and he had no reason to think otherwise. Fast forward, and I use that phrase intentionally, to Isaac Newton. Now, Newton is one of those figures who's so famous that it's easy to forget just how radical his ideas were when he first published them. In 1687, he put out the Principia Mathematica, which is one of those books that genuinely changed the trajectory of human civilization. And in it, Newton laid out his laws of motion and his theory of gravity, and to make all of that work, he needed a very specific concept of time. He called it absolute time. Here's what he wrote, and I'm paraphrasing slightly, but the gist is this: absolute, true, and mathematical time, of itself and from its own nature, flows equably without relation to anything external. Read that again in your mind. Time flows equably, meaning evenly, steadily, without relation to anything external. It doesn't care what's happening in the universe. It doesn't care how fast you're moving or where you are or how much gravity is pulling on you. time just flows. It's like a backdrop, a stage on which everything else happens, but the stage itself never changes. And this worked. It worked incredibly well. Newton's physics, built on this foundation of absolute time, could predict the motions of planets, the trajectories of cannonballs, the behavior of tides. For over 200 years, Newtonian mechanics was the gold standard of physics. Engineers used it to build bridges and steam engines and railways. Astronomers used it to predict eclipses down to the minute. And all of it rested on this assumption that time is universal, constant, the same everywhere, and for everyone. There was no time travel in Newton's universe, not really. There was just the steady, implacable forward march of absolute time, and you were along for the ride whether you liked it or not. But here's the thing. Even within Newton's framework, there were hints, little cracks in the foundation, that most people didn't notice or didn't think were important. Newton's laws of motion have a peculiar property. They're time-symmetric. That's a term worth understanding, because it comes up again and again in physics. What it means is this. If you take Newton's equations and replace every instance of time, the variable t, with negative t, essentially running the clock backward, the equations still work perfectly. They're just as valid. A ball thrown upward and coming back down looks exactly the same whether you play the film forward or backward. The math doesn't care which direction time is going. The equations themselves don't have a preference for the future over the past. Now, that's weird, right? Because our experience of time is deeply asymmetric. Eggs break, but don't unbreak. You get older, but never younger. You remember yesterday, but not tomorrow. There's a very clear arrow pointing from past to future in our lived experience. But Newton's fundamental laws don't contain that arrow. They work just as well in reverse. This was a puzzle that wouldn't be fully appreciated for another couple of centuries, but it's worth planting the seed now because it's going to matter a lot when we get to the deeper physics. The laws of the universe, at their most fundamental level, don't seem to care about the direction of time. So where does our sense of time's direction come from? Hold that thought. We'll come back to it. Now, while Newton's absolute time was reigning supreme, there was at least one prominent voice pushing back, and that was Gottfried Wilhelm Leibniz. Leibniz, who independently invented calculus around the same time as Newton. And yes, that led to one of the most bitter intellectual feuds in the history of science. But that's a story for another night. Leibniz had a fundamentally different view of time. He argued that time isn't a thing in itself. It's not a container or a backdrop. Time, Leibniz said, is just a way of describing the order of events. It's relational. If nothing happens, there's no time. Time is just the word we use for the fact that some things happen before other things, and some things happen after. It's a relationship between events, not an independent entity. This might sound like a minor philosophical distinction, but it's actually enormous. Because if time is absolute, the way Newton said, then asking what happened before the universe began is a meaningful question. There was time before there was stuff. But if time is relational, the way Leibniz argued, then that question doesn't even make sense. No events, no time. The debate between these two views, is time a thing, or is it just a description of relationships between things, has never been fully resolved. It's still alive in modern physics. And it matters for time travel, because your answer to that question shapes what you think time travel even means. If time is a real thing, a dimension you can move through, then maybe you can move backward through it, just like you can move backward through space. But if time is just the ordering of events, then traveling backward in time might be as meaningless as traveling north of the North Pole. But let's not get too abstract too quickly. Let's stay in the story. Because what happened next in the history of physics is one of the most dramatic intellectual revolutions ever, and it starts with a young man working in a patent office in Bern, Switzerland, in 1905. You know who I'm talking about. Albert Einstein was 26 years old. He hadn't been able to get an academic position. He'd been rejected, overlooked, and was spending his days evaluating patent applications for electromagnetic devices. And in his spare time, he was about to demolish Newton's concept of absolute time and replace it with something so strange, so counterintuitive, that physicists are still working out all the implications more than a century later. The paper was called On the Electrodynamics of Moving Bodies, which is maybe the most understated title in the history of science, given what it contains. And the core idea, the one that changes everything, starts with a question that sounds almost childish. What does it mean for two events to happen at the same time? Think about that. You're lying in bed, and somewhere across town, a street light turns on. Did those two things, you lying down, the light turning on, happen at the same time? Well, sure, maybe. But how would you know? You'd have to see the light, or receive some signal from it, and that signal takes time to travel to you. Light is fast, incredibly fast, about 300 million meters per second, but it's not infinitely fast. There's always a delay. And Einstein realized that this isn't just a practical inconvenience. It's a fundamental feature of reality. The concept of at the same time, simultaneity, physicists call it, isn't absolute. It depends on who's asking and how they're moving. Here's the thought experiment that makes it click. Imagine you're standing on a train platform, and a train is zooming past you. Right at the moment the middle of the train passes you, two lightning bolts strike. One hits the front of the train, one hits the back, at the exact same instant from your perspective. You see both flashes at the same time because you're equidistant from both strikes. So you say, those were simultaneous. But now, think about what the person sitting in the middle of the train sees. The train is moving forward, so after the lightning strikes, that person is moving toward where the front strike happened and away from where the back strike happened. The light from the front strike reaches them first. The light from the back strike reaches them a tiny bit later. And here's Einstein's key move. Since the speed of light is the same for everyone, it doesn't matter if you're moving toward the source or away from it, light always travels at the same speed. The person on the train has every right to conclude that the front strike happened first. Not that they saw it first, but that it actually happened first. Two observers watching the same two events, and they genuinely disagree about whether those events happened at the same time. And neither one is wrong. They're both right within their own frame of reference. Simultaneity is relative. And if simultaneity is relative, then time itself is relative. The steady, universal, absolute time of Newton, the time that flows equably without relation to anything external, doesn't exist. It never did. Time is personal. Time is local. Your time and my time don't have to agree, and under the right circumstances they won't. This is special relativity, and it has a specific measurable consequence that sounds like pure science fiction, but has been confirmed by experiments over and over and over again. It's called time dilation, and here's how it works. The faster you move relative to someone else, the slower your time passes relative to theirs. Not metaphorically, not as an illusion. Your clocks literally tick slower. Your biological processes run slower. everything about your experience of time slows down, and you don't notice it. From your perspective, everything feels perfectly normal. It's only when you compare your clock to the clock of someone who wasn't moving with you that you see the difference. The numbers are real. In 1971, two physicists named Joseph Haffel and Richard Keating put incredibly precise atomic clocks on commercial airliners and flew them around the world, eastward and westward, then compared them to identical clocks that stayed on the ground at the United States Naval Observatory. And the clocks disagreed. By tiny amounts, billionths of a second, but exactly the amounts that Einstein's equations predicted. Time had passed at different rates for the traveling clocks and the stationary ones. The clocks on the planes had, in a very real and measurable sense, traveled into the future by a tiny, tiny amount compared to the clocks on the ground. And that's not even the most dramatic version. We have particles called muons that are created when cosmic rays hit the upper atmosphere. Muons are unstable. They decay, they fall apart, and they do it fast. Their half-life is about 2.2 microseconds. At the speed of light, that means they should only be able to travel about 600 meters before they decay. But the upper atmosphere is tens of kilometers above us, so muons created up there should never reach the ground. They should decay long before they get here. But they do reach the ground. We detect them all the time, and the reason is time dilation. Those muons are moving at nearly the speed of light, and at that speed, time slows down for them so dramatically that their brief 2-microsecond lifetime gets stretched out, from our perspective, long enough for them to make the whole journey down to the surface. From the moon's perspective, it lives its normal short life. But from our perspective, its clock is running slow, and it survives the trip. So here's where we are. It's 1905, and a 26-year-old patent clerk has just shown that time is not what we thought it was. It's not universal. It's not constant. It bends and stretches depending on how fast you're moving. And if you could move fast enough, close enough to the speed of light, you could experience 1 year while everyone else experiences 100. You'd step off your spaceship and everyone you knew would be gone. Their great-grandchildren would be old. You would have traveled into the future, genuinely, irreversibly. And there's nothing in physics that says you can't do it. The only barrier is engineering, building something that can go that fast, but that's only half the story. Because 10 years later, Einstein published something even more revolutionary, something that would take time dilation and turn it inside out, and it has to do with gravity. In 1915, he completed his general theory of relativity, and what it says about time is so strange that even Einstein himself found it unsettling, because it turns out that speed isn't the only thing that warps time. Mass does it too. The heavier an object is, the more it curves the fabric of space-time around it, and that curvature doesn't just affect space, it affects time. Clocks tick slower in stronger gravitational fields. A clock on the ground floor of a building runs ever so slightly slower than a clock on the top floor, because the ground floor is closer to the Earth's center of mass, where gravity is slightly stronger. And this isn't theoretical. The GPS satellites orbiting Earth right now have to correct for this effect. Their atomic clocks tick faster than clocks on the surface by about 38 microseconds per day, and if the software didn't account for that, your GPS position would drift by kilometers. Every time you use your phone to navigate to a restaurant, you are relying on Einstein's corrections to Newton's absolute time. And general relativity opens a door that special relativity only hinted at. Because if mass warps time, then enough mass, concentrated enough, could warp time in truly extreme ways. And that leads us to one of the strangest objects in the universe. Something that even the physicists who first predicted it didn't quite believe could be real. It leads us to black holes, and to the first serious mathematical hints that time might not just slow down or speed up, but might, under the right conditions, actually do something truly bizarre. Because when Karl Schwarzschild, a German physicist and astronomer, sat down with Einstein's brand new field equations in 1916, just months after general relativity was published, he wasn't in a university office or a comfortable study. He was on the Eastern Front of World War I, serving in the German army, calculating artillery trajectories during the day, and, somehow, working through the most complex mathematical physics of his era at night. And what he found, while literally stationed in a war zone, was the first exact solution to Einstein's equations. He sent his results to Einstein in a letter, and Einstein was reportedly stunned by the elegance of it. What Schwarzschild described was what happens to space-time around a perfectly spherical, non-rotating mass, and buried in his solution was a peculiar feature. At a certain distance from the center of that mass, a boundary appeared where something very strange happened. The math showed that at this radius, which we now call the Schwarzschild radius, the curvature of space-time became so extreme that nothing, not light, not information, not anything, could escape from inside it. Cross that boundary, and you're falling inward forever. Now, Schwarzschild himself didn't fully appreciate what his solution implied. He died just a few months later, in May of 1916, from a disease he contracted on the front. He was only 42, and for decades after his death, most physicists treated that strange boundary in his equations as a mathematical curiosity, maybe even a flaw. Einstein himself was deeply skeptical that nature would actually produce such an object. He wrote a paper in 1939 arguing that matter could never collapse to that degree. The idea seemed too extreme, too alien. But the math didn't care about anyone's comfort level. Here's the thing about the Schwarzschild solution that matters for our conversation about time. As you get closer and closer to that boundary, what we now call the event horizon, time dilation becomes more and more extreme. Remember how we talked about clocks running slower in stronger gravitational fields? Well, near a black hole, gravity is so intense that this effect goes haywire. If you were watching someone fall toward a black hole from a safe distance, you'd see them slow down. Their movements would become sluggish. Their watch would seem to tick slower and slower. As they approached the event horizon, they'd appear to almost freeze, their image reddening and dimming as the light they emit gets stretched by the warping of space-time. From your perspective, they never quite cross the boundary. They just fade away, stuck in an eternal slow-motion approach. But from their perspective, and this is the part that really bends your mind, everything is fine. They cross the event horizon without even noticing it. Their watch ticks normally. They don't feel time slowing down. They just keep falling. The experience of time is completely different depending on who's doing the experiencing. And once they're inside, the math says something genuinely unsettling. Inside the event horizon, the roles of space and time effectively swap. The direction toward the center of the black hole isn't really a direction in space anymore. It becomes a direction in time. Falling toward the singularity isn't like moving through space. It's like moving forward through time. It's inevitable, in the same way that tomorrow is inevitable for you right now. You can't turn around and go back any more than you can turn around and go back to yesterday. So already, with black holes, we're seeing time do things that Newton never could have imagined. Time isn't just slowing down or speeding up, it's being restructured. The very geometry of time is different inside that boundary. And this was all sitting there in Schwarzschild's equations from 1916, waiting for people to take it seriously. It took a while. Through the 20s and 30s, a handful of physicists poked at the problem. In 1931, Subrahmanyan Chandrasekhar, a young Indian physicist who was literally on a boat from India to England to begin his graduate studies at Cambridge, worked out that stars above a certain mass, about 1.5 times the mass of our sun, couldn't support themselves against gravitational collapse once they exhausted their nuclear fuel. There was no known force that could hold them up. This was a stunning result, and when Chandrasekhar presented it, he was publicly ridiculed by Arthur Eddington, one of the most prominent astrophysicists of the era. Eddington essentially said that nature must have some way of preventing such a collapse, that the conclusion was absurd. He didn't have a physical argument for why it couldn't happen. He just found it aesthetically offensive. And Chandrasekhar, who was barely in his 20s, was so discouraged by this public humiliation that he largely moved on to other problems. He wouldn't receive the Nobel Prize for this work until 1983, more than 50 years later. But Chandrasekhar was right. And in 1939, Robert Oppenheimer, yes, the same Oppenheimer who would later lead the Manhattan Project, along with his student Hartland Snyder, published a paper showing exactly what happens when a massive star collapses. They demonstrated that from an outside observer's perspective, the star's surface would slow down as it approached the Schwarzschild radius, appearing to freeze at the event horizon. But from the perspective of someone riding the surface of the star, the collapse would continue right through the event horizon and onward toward a point of infinite density. Time, once again, behaving completely differently depending on where you're standing. And then the war came, and Oppenheimer went off to build the bomb, and the whole question of gravitational collapse got shelved for about 20 years. It wasn't until the late 1950s and 1960s that physicists really returned to these ideas with fresh eyes, and when they did, things got even stranger. In 1963, a New Zealand mathematician named Roy Kerr found something remarkable. Schwarzschild's original solution described a non-rotating black hole, but real objects in the universe spin. Stars spin, planets spin, galaxies spin. Angular momentum is everywhere. So Kerr worked out what Einstein's equations predicted for a rotating black hole, and his solution contained a feature that nobody expected. Inside a rotating black hole, the singularity wasn't a point. It was a ring of infinite density, spinning in space. And if you could somehow pass through that ring instead of hitting it, the math suggested you'd emerge into a different region of space-time entirely. Not just a different place, but potentially a different time. Kerr's solution contained what looked like pathways, trajectories through space-time that looped around and came out somewhere else, maybe even someone else. Now, you might be thinking, okay, so the math allows it, but does that mean it's real? And that's exactly the right question, because this is where we hit one of the deepest tensions in theoretical physics. The equations of general relativity are extraordinarily well tested. They predict the bending of light around massive objects, the existence of gravitational waves, the precise orbit of Mercury, the behavior of GPS satellites, all confirmed to remarkable precision. So when those same equations also predict something as wild as a pathway through a rotating black hole that could connect different times, you can't just wave it away. You have to take it seriously, even if you're uncomfortable with the implications. And this is where we meet one of the most fascinating characters in the whole story of time travel physics. His name was Kurt Gödel, and he wasn't a physicist at all. He was a logician, maybe the greatest logician since Aristotle. Gödel is most famous for his incompleteness theorems, which shook the foundations of mathematics in 1931 by proving that any consistent mathematical system complex enough to describe basic arithmetic must contain statements that are true but unprovable within that system. It's one of the most profound results in the history of human thought, and it's worth pausing on for just a moment, because the kind of mind that produced that result is exactly the kind of mind that would look at Einstein's equations and find something everyone else had missed. Gödel and Einstein were colleagues at the Institute for Advanced Study in Princeton in the 1940s. They were close friends, actually, an unlikely pair, the rumpled, genial Einstein and the thin, intensely private Gödel, who was so paranoid about being poisoned that he would only eat food prepared by his wife. They walked to and from the institute together almost every day, and Einstein reportedly said that in his later years he went to the office mainly for the privilege of walking home with Gödel. In 1949, Gödel presented Einstein with a birthday gift that was also, in a way, a philosophical bomb. He had found a new solution to Einstein's field equations, a model of a universe that was rotating, a universe where all the matter in it was slowly spinning around a common axis. And in Gödel's rotating universe, something extraordinary was true. There existed paths through space-time, perfectly valid trajectories that obeyed all the laws of physics, that looped back on themselves. They were closed curves in time. If you traveled along one of these paths, you would eventually return to your own past, not metaphorically, not in some vague, hand-wavy sense. Mathematically, rigorously, within the framework of general relativity, Gödel had shown that a universe could exist in which time travel to the past was physically possible. Think about what that means. This wasn't science fiction. This wasn't speculation. This was a valid solution to the most well-tested theory of gravity and space-time we have. Gödel had used Einstein's own equations to show that the past could, in principle, be revisited. Einstein was troubled by this, deeply troubled. He acknowledged that Gödel's math was correct. There was no error in the solution. But he hoped and wrote that the physical conditions required for Gödel's universe, a universe uniformly rotating, didn't match our actual universe. And he was right about that. Our universe doesn't appear to be rotating in the way Gödel described. But that almost misses the point, because Gödel's argument wasn't really about whether our specific universe allows time travel. His argument was more subtle and more devastating. He was saying, if the laws of physics, Einstein's laws, permit any universe where time travel is possible, then time as we experience it, as this inexorable flow from past to future, cannot be a fundamental feature of reality. It must be, in some sense, an illusion, a feature of our particular arrangement of matter and energy, not a deep truth about the nature of existence. And that idea, that time might be less fundamental than we think, that our experience of its passage might be something like an artifact of our perspective rather than a built-in feature of the cosmos, that idea has haunted physics ever since. It connects back to something we touched on earlier, that puzzle about why the laws of physics don't seem to care about the direction of time, even though we so obviously do. Gödel's rotating universe made that puzzle sharper, more urgent, more personal. But Gödel's closed timelike curves, as they came to be called, also opened a Pandora's box of logical problems. Because if you can travel to your own past, then you can potentially change it. And if you can change it, you run into paradoxes, the kind of paradoxes that have fueled 1,000 science fiction stories, but that also represent genuine, unresolved problems in theoretical physics. And the most famous of these paradoxes has a name you've almost certainly heard, even if you've never thought about it in a physics context. It's called the grandfather paradox, and it goes like this. Suppose you travel back in time, and, through some chain of events, you prevent your own grandfather from meeting your grandmother. Then your parent is never born, and then you are never born. And then you never travel back in time, which means your grandfather does meet your grandmother, which means you are born, which means you do travel back in time, which means, and you see the problem. It's a logical loop with no consistent resolution, at least not an obvious one. Now, you might think this is just a silly thought experiment, a game for philosophers. But here's why physicists take it seriously. If the laws of physics genuinely permit closed timelike curves, and Gödel showed that general relativity does, at least in some solutions, then those laws need to be consistent. Physics doesn't tolerate contradictions. The universe doesn't crash like a computer program encountering a divide-by-zero error. So either closed timelike curves are somehow forbidden by some deeper principle we haven't found yet, or there's a way to resolve the paradoxes that we haven't fully understood. And several brilliant physicists have proposed some really fascinating answers. Let's walk through them, because each one tells you something deep about how the universe might actually work. The first serious proposal came from a physicist named Igor Novikov, working in the Soviet Union during the 1970s and 1980s. Novikov is one of those figures who deserves to be far more famous than he is outside of physics circles. He was a brilliant relativist, a student of Yakov Zeldovich, who was himself one of the great astrophysicists of the 20th century. And Novikov looked at the grandfather paradox and said, essentially, you're thinking about this wrong. You're assuming that if you travel to the past, you have the freedom to change it. But what if you don't? What if the laws of physics constrain events on a closed timelike curve so that everything remains self-consistent, no matter what? This became known as the Novikov self-consistency principle, and it's one of those ideas that sounds almost too simple at first, but gets more profound the longer you sit with it. Here's the core claim. If closed timelike curves exist, then the only events that can occur on them are events that are globally self-consistent. In other words, you can travel to the past, but you cannot create a paradox, because the universe simply won't let you. Whatever you do in the past was always part of the history that led to your existence in the first place. Think about what that means. You go back in time intending to prevent your grandparents from meeting, but something happens. You trip. You get lost. You accidentally introduce them to each other instead. Or maybe you do exactly what you planned, but it turns out your grandmother was already pregnant, or your grandfather wasn't actually your biological grandfather, or some other twist that preserves the consistency of the timeline. The point isn't that some magical force stops you. The point is that the initial conditions of the universe, the boundary conditions of space-time itself, are such that paradoxical outcomes simply aren't among the physically possible histories. Now, if you're lying there thinking, wait, doesn't that mean I don't have free will? Yeah, that's exactly the question that comes up, and it's a deep one. Novikov's principle doesn't necessarily eliminate free will in the philosophical sense, but it does constrain it in a way that feels uncomfortable. You're free to try anything you want, but the outcomes are predetermined to be consistent. It's a bit like being free to throw a ball in any direction, but the laws of gravity guarantee it will come back down. You have freedom of action, but the laws of physics determine the result. On a closed, timelike curve, those laws are just more restrictive than you might expect. And here's the thing. Novikov's principle isn't just hand-waving. In the early 1990s, a group of physicists, including Novikov himself, along with several others, actually worked through the mathematics of simple physical systems on closed, timelike curves. They looked at things like billiard balls traveling through wormholes. We'll get to wormholes soon, I promise. And they showed that for every apparently paradoxical setup, there existed at least one self-consistent solution. Often there were multiple self-consistent solutions. The math worked. The physics didn't break. The paradoxes dissolved, not because time travel was forbidden, but because the paradoxical versions of events simply weren't solutions to the equations. That's a remarkable result. But it raises its own questions, the biggest being: if there are multiple self-consistent histories, which one actually happens, and who or what chooses? That question remains genuinely open. So that's one approach: self-consistency. The universe polices itself. But there's another approach that comes from a completely different direction, and it involves one of the most mind-bending ideas in all of physics. This is the many worlds interpretation of quantum mechanics, and the physicist most associated with applying it to time travel is David Deutsch. Now, David Deutsch is a fascinating character in his own right. Born in Haifa in 1953, he ended up at Oxford, where he became one of the founders of quantum computation. Literally, one of the people who figured out that quantum mechanics could be used to build a fundamentally new kind of computer. But Deutsch is also a deep thinker about the foundations of physics, the kind of person who isn't satisfied with just calculating answers, but wants to understand what the equations are actually telling us about reality. And in 1991, he published a paper that tackled the grandfather paradox head-on, using the many worlds framework. Here's the basic idea. In the many worlds interpretation of quantum mechanics, which was originally proposed by Hugh Everett in 1957, and that's a whole story in itself, every time a quantum event has multiple possible outcomes, the universe doesn't pick just one. Instead, all outcomes occur, each in its own branch of an ever-splitting reality. So there isn't one universe. There's an inconceivably vast number of parallel universes, all equally real, all coexisting in some higher dimensional sense. Deutsch took this framework and applied it to closed timelike curves, and what he found was striking. In the many worlds picture, when you travel back in time, you don't arrive in your own past. You arrive in a different branch of reality, a parallel universe that is identical to your past up to the moment of your arrival, but that can then diverge. So you can prevent your grandfather from meeting your grandmother in that branch. And there's no paradox, because in the branch you came from, your grandfather did meet your grandmother. You were born, and you did travel back in time. The two branches are consistent within themselves. The paradox evaporates because the causal loop is broken. You're not actually in your own past. You're in a copy. Now this is a very different resolution from Novikov's. Novikov says there's one timeline and it's self-consistent. Deutsch says there are many timelines and you can hop between them. Both are mathematically coherent. both are consistent with the known laws of physics, at least at the level of our current understanding. And we don't currently have a way to determine which one is correct, because we don't have a working theory of quantum gravity, which is what you'd need to really nail this down. But here's what's really interesting about Deutsch's approach. It connects time travel to quantum computing in a deep way. Deutsch showed that a quantum computer with access to a closed timelike curve could solve problems that are believed to be unsolvable even by ordinary quantum computers. It could, in a sense, send information back to itself and use that to shortcut calculations. This isn't just science fiction speculation. It's a result with precise mathematical content, and it suggests that if closed time-like curves exist, they would have profound implications not just for physics, but for the theory of computation itself, for what is and isn't possible to calculate in this universe. So we have two proposals on the table: self-consistency and many worlds. But there's a third approach, and it's the most conservative one. Maybe closed time-like curves simply can't exist. Maybe there's a law of physics, one we haven't fully formulated yet, that prevents them from forming. And the person most associated with this view is Stephen Hawking. In 1992, Hawking proposed what he called the chronology protection conjecture, and I love the way he phrased it. He said the laws of physics conspire to prevent time travel by macroscopic objects. Conspire. As if the universe is actively working to keep you from going back and messing things up. Hawking wasn't being whimsical, though. He had specific physical reasons for this conjecture. The basic argument goes like this. To create a closed time-like curve, you need to warp space-time in very extreme ways. And when you try to do that, quantum effects, specifically the behavior of quantum fields in curved space-time, tend to produce enormous amounts of energy near the region where the time loop would form. This energy, Hawking argued, would grow without bound, becoming infinite right at the moment the closed time-like curve would come into existence, effectively destroying the time machine before it could be used. The universe protects chronology by blowing up your time machine with quantum energy. It's an elegant idea, and there's real physics behind it. Calculations by Hawking and others showed that in many specific scenarios, quantum field effects do indeed diverge near chronology horizons, the boundaries in space-time where closed time-like curves would begin to form. But here's the catch. Those calculations were done using quantum field theory in curved space-time, which is a semi-classical approximation. It's not the full theory of quantum gravity, and the divergences occur precisely in the regime where that approximation breaks down, where you'd really need the full theory to know what happens. So Hawking's conjecture remains a conjecture. It hasn't been proven. And Hawking himself acknowledged this. He said he couldn't prove it, because we don't have a complete theory of quantum gravity. He was betting on the outcome, not demonstrating it. And that bet, that wager about what a future theory will say, is itself a fascinating window into how theoretical physics works at the frontier. Sometimes the best you can do is make an educated guess and see if the universe agrees. Now, what's beautiful about this three-way debate? Novikov's self-consistency, Deutsch's many worlds, Hawking's chronology protection, is that each one reflects a different philosophical attitude toward physics. Novikov trusts general relativity and says the universe is self-consistent. Deutsch trusts quantum mechanics and says reality is bigger than we think. Hawking trusts that nature is conservative and says the exotic stuff probably can't happen. And all three of these positions are held by serious, brilliant physicists who understand the mathematics deeply. The fact that they disagree tells you something important. This is a genuinely open question. We don't know the answer. And the reason we don't know is that the answer almost certainly requires a theory that unifies general relativity and quantum mechanics, a theory of quantum gravity that we don't yet have. But while the paradox debate was playing out in the 1990s, something else was happening in parallel. Physicists were getting more creative about the actual mechanisms of time travel, not just whether it was logically consistent, but how you might actually build a time machine. And this brings us to one of the most remarkable objects in all of theoretical physics, something that had been hiding in the equations of general relativity since the 1930s, but didn't get taken seriously as a potential time machine until much later. I'm talking about wormholes, those tunnels through space-time that connect distant points, and that, under the right conditions, might also serve as shortcuts through time itself. So let's talk about them properly, because the story of wormholes is one of the strangest detours in the history of physics. The idea starts, like so many things, with Einstein. In 1935, Einstein and his collaborator Nathan Rosen published a paper that was trying to solve a completely different problem. They weren't thinking about time travel at all. They were bothered by singularities, those points in general relativity where the math blows up, where density becomes infinite and the equations stop making sense. Specifically, they were looking at the Schwarzschild solution, the one we talked about earlier, the geometry around a perfectly spherical mass, and they noticed something curious. If you took the Schwarzschild geometry and extended it mathematically, you could connect two copies of flat space-time through a kind of bridge, a throat joining two separate regions. Einstein and Rosen thought this might be a way to model elementary particles, to avoid the troublesome singularity by replacing it with this smooth geometric connection. That idea didn't really pan out for particle physics, but the mathematical structure they found was real, and it eventually got a name: the Einstein-Rosen bridge. Today we call it a wormhole, a term coined much later by the physicist John Archibald Wheeler in 1957. Wheeler had a gift for naming things. He's also the one who popularized the term black hole, and wormhole stuck because of the analogy with a worm eating through an apple. Imagine an ant on the surface of an apple. To walk from one side to the other, the ant has to crawl all the way around the curved surface. But if a worm has bored a tunnel straight through the apple, the ant could take a shortcut through the interior. That's the basic idea. A wormhole is a tunnel through the interior of space-time that connects two points that might be very far apart on the surface. Now, here's the thing about the Einstein-Rosen bridge specifically. It's not actually traversable. If you try to travel through it, it pinches off too quickly. It opens and closes so fast that not even light can get through. So for decades, wormholes were considered a mathematical curiosity, interesting in the equations, but physically useless. Nobody could travel through one. They were like doors that slam shut before you can step through. That changed in 1988, and the way it changed is one of my favorite stories in all of physics. It starts not with a physicist, but with a novelist. Carl Sagan, the astronomer, the science communicator, the man behind Cosmos, was writing his novel, Contact. He needed a scientifically plausible way to move his character, Ellie Arroway, across the galaxy quickly. He'd originally written something about her traveling through a black hole, but he wanted to get the physics right. So he called up his friend Kip Thorne at Caltech and asked for help. Now, Kip Thorne is one of the leading experts on general relativity in the world. He would later win the Nobel Prize in 2017 for the detection of gravitational waves. And when Sagan asked him this question, how could someone realistically travel across the galaxy? Thorne didn't just dash off a quick answer. He took the question seriously as a physics problem. He sat down with his graduate students, Michael Morris being the key one, and they asked, what would it take to have a wormhole that a person could actually travel through safely? The paper they published in 1988, Morris and Thorne, is a landmark. It's called Wormholes in Space-Time and Their Use for Interstellar Travel, and it reads almost like an engineering specification. They worked out the geometry of a traversable wormhole, one that stays open long enough for someone to pass through, one where the tidal forces won't tear you apart, one with no event horizon blocking the entrance. And they found that such a thing is mathematically possible within general relativity. The equations allow it. But, and this is a big but, it requires something called exotic matter. Let's talk about what that means, because it's crucial. In general relativity, the geometry of space-time is determined by the matter and energy present. Normal matter and energy curve space-time in familiar ways. They create gravity that pulls things together. But to hold a wormhole open, you need matter that has negative energy density. Think of it this way. Normal gravity pulls the walls of the wormhole throat together, trying to pinch it shut, just like the Einstein-Rosen bridge. To keep the throat open, you need something that pushes outward, something that acts like anti-gravity at the throat of the wormhole. That requires energy that is, in a precise technical sense, negative. And that's what exotic matter is, matter or fields that violate what physicists call the energy conditions, the usual assumptions about how energy behaves. Now, you might think negative energy is pure fantasy, but here's what's wild. It actually exists in small quantities. The Casimir effect, discovered theoretically by Hendrik Casimir in 1948 and confirmed experimentally in 1997 by Steve Lamoureux, shows that the quantum vacuum between two very closely spaced metal plates has less energy than the vacuum outside. The energy density between the plates is effectively negative. It's a tiny, tiny effect. We're talking about incredibly small amounts of negative energy, but it's real. Quantum mechanics allows it. So the exotic matter that Thorne's wormhole needs isn't completely ruled out by physics. The question is whether you could ever get enough of it, concentrated in the right way, to actually prop open a wormhole. And that's where things get really speculative, because the amounts you'd need are, by most estimates, astronomical. Some calculations suggest you'd need negative energy equivalent to the mass of Jupiter, focused into a thin shell around the wormhole throat. That's not something we have any idea how to create. But let's set aside the engineering impossibility for a moment, because the theoretical implications are what matter for our story. What Thorne and Morris showed is that if you could build a traversable wormhole, if you could somehow get your hands on enough exotic matter, then you could also, in principle, turn it into a time machine. And the method is surprisingly elegant. Here's how it works. Imagine you have a wormhole with two mouths, two openings connected by this short tunnel through space-time. Call them mouth A and mouth B. Now, take mouth B and accelerate it to a very high speed, close to the speed of light, and then bring it back. Remember special relativity? The moving mouth experiences time dilation. Less time passes for mouth B than for mouth A. So when you bring mouth B back and set it down next to mouth A, the two mouths are now at different times. If mouth A has experienced, say, 10 years, and mouth B has experienced only 1 year due to time dilation, then stepping into mouth A and walking through the tunnel would bring you out of mouth B. But 9 years in the past, you've created a time difference between the two ends of the wormhole. The tunnel itself is short, maybe just a few meters long, but it connects two different moments in time. That's a time machine. Alternatively, you could use gravity instead of velocity. Take mouth B and park it near a massive object, a neutron star, say, or close to a black hole. Gravitational time dilation slows down the clock at mouth B relative to mouth A. Same result. After a while, the two mouths are at different times, and the wormhole becomes a bridge not just through space, but through time. Think about what that means. You wouldn't need to travel at impossible speeds. You wouldn't need infinite energy. You'd need exotic matter, which is exotic indeed. But the mechanism for creating the time difference is just ordinary relativity, the same time dilation we've already confirmed with atomic clocks on airplanes and GPS satellites. The speculative part is the wormhole itself. The time machine part is, in a sense, the easy part. This is what got people so excited in the late 1980s and early 1990s. For the first time, there was a concrete, step-by-step proposal for how a time machine might actually work within the known laws of physics, not a vague possibility hidden in the mathematics, like Gödel's rotating universe, which required the entire cosmos to be spinning in a way that ours clearly isn't. Not a journey through the interior of a rotating black hole, which would probably kill you and might not even be stable. This was a clean, almost engineering-style proposal. Build a wormhole, move one mouth, wait, step through. You've traveled in time. And it was precisely this proposal that prompted Hawking to formulate his chronology protection conjecture. Remember, Hawking's argument was that quantum effects would destroy the wormhole just as it was about to become a time machine. The vacuum fluctuations, those tiny quantum fields that are always present everywhere in space, would circulate through the wormhole, looping from one mouth to the other and back again, piling up energy each time around. As the wormhole approaches the moment when it would first allow a closed, timelike curve, this energy buildup would diverge, become infinite, and the resulting back reaction would either collapse the wormhole or tear it apart. Nature censors itself. The time machine self-destructs just before it switches on. But as we discussed, Hawking's argument relies on semi-classical gravity, using quantum field theory on a fixed, curved background without fully accounting for how the quantum fields change the geometry itself. And right at the moment when the energy is diverging, right at the chronology horizon, that approximation breaks down. You'd need full quantum gravity to say what really happens. So the question remains genuinely open. Now, there's another twist to the wormhole story that's worth lingering on, because it connects to some of the deepest questions in modern physics. In 2013, Juan Maldacena and Leonard Susskind proposed something remarkable. They suggested that Einstein-Rosen bridges, wormholes, might be the same thing as quantum entanglement. Their slogan was ER equals EPR, ER for Einstein-Rosen, the wormhole paper of 1935, EPR for Einstein-Podolsky-Rosen, the quantum entanglement paper, also from 1935. Two papers from the same year, by some of the same authors, describing what seemed like completely unrelated phenomena, and Maldacena and Susskind were suggesting they might be two descriptions of the same underlying reality. The idea is still speculative, still being developed, but if it's right, it means that the connection between two entangled particles, that spooky correlation that Einstein himself was so uncomfortable with, is actually a tiny, non-traversable wormhole connecting them through space-time. Every pair of entangled particles, everywhere in the universe, linked by a microscopic thread of space-time geometry. It's a breathtaking idea, and it hints at something profound, that space-time itself might be stitched together by entanglement, that the smooth, continuous fabric of space we experience might emerge from a vast web of quantum correlations connecting everything to everything else. And if that's true, then wormholes aren't just exotic curiosities or hypothetical time machines. They're the fundamental building blocks of reality itself, which means that understanding them, understanding whether they can be traversable, whether they can be stabilized, whether they really do connect to entanglement, isn't just about time travel. It's about understanding what space-time actually is at the deepest level. This is where the story of time travel starts to merge with the biggest open question in all of theoretical physics: quantum gravity. And one of the most promising approaches to that question, the one that Maldaceno's work grows out of, involves something called the holographic principle, and a correspondence that connects gravity in higher dimensions to quantum field theory in lower dimensions. It sounds abstract, and it is, but it has surprisingly concrete things to say about whether time travel is possible. And it starts with a discovery that Maldaceno made in 1997 while working at the Institute for Advanced Study in Princeton, the very same institution where Einstein and Gödel used to take their walks together, which is a lovely piece of continuity if you think about it. Juan Maldacena was a young Argentine physicist, barely 30 years old, and he was wrestling with one of the deepest problems in theoretical physics: how to reconcile general relativity, Einstein's theory of gravity and curved spacetime, with quantum mechanics, the theory that governs everything at the smallest scales. These two frameworks are each spectacularly successful in their own domain. But when you try to combine them, when you try to describe what happens to space-time itself at quantum scales, or what's really going on at the center of a black hole, or what happened at the very first instant of the Big Bang, they produce nonsense. Infinities crop up everywhere. The math breaks down, and for decades, nobody could figure out how to fix it. String theory was one of the most ambitious attempts, and by the mid-1990s, it had developed into a rich and elaborate mathematical framework, but it was also notoriously difficult to extract concrete predictions from. What Maldacena did in 1997 was discover a remarkable relationship, a duality, physicists call it, between two seemingly unrelated theories. On one side, you have a theory of gravity operating in a particular kind of curved space-time called anti-de Sitter space. Think of it as a universe with a specific geometric shape. It has a boundary, an edge, and the interior is curved in a very particular way that's different from our own universe, but mathematically very tractable. On the other side, you have a quantum field theory. No gravity at all, just particles and fields interacting. But this theory lives on the boundary of that space, one fewer dimension, like a hologram. And here's what Maldacena showed, or more precisely conjectured with overwhelming mathematical evidence. These two theories are exactly equivalent, not approximately, not analogously. They are the same theory, written in two completely different languages. Everything that happens in the gravitational theory in the interior, black holes forming, space-time curving, objects falling, has an exact translation into the non-gravitational quantum theory on the boundary, and vice versa. This is the ADS/CFT correspondence, sometimes called the Maldacena duality, and it's probably the single most important result in theoretical physics in the last 30 years. Now, you might be wondering what on earth this has to do with time travel. Fair question. Let's get there. But first, let me help you feel why this result matters so much. Because it's genuinely one of those ideas that changes how you think about reality once you absorb it. Imagine you have a snow globe. Inside the snow globe, there's a little three-dimensional world with gravity. Things fall, objects attract each other, space-time curves. Now imagine that everything happening inside that snow globe is perfectly, completely, exactly encoded on the two-dimensional surface of the glass. Every event, every particle trajectory, every gravitational interaction inside the globe has a corresponding description as a pattern on the surface. The surface description doesn't look anything like gravity. It's just quantum fields fluctuating, particles interacting through forces that aren't gravity at all. But it contains all the same information. If you were a being living on the surface, you could in principle reconstruct everything happening inside the globe just from the patterns around you. That's the holographic principle in a nutshell. The word holographic comes from actual holograms, those shiny images on credit cards that encode three-dimensional information on a two-dimensional surface. The idea was first proposed by Gerard 't Hooft in 1993 and developed by Leonard Susskind, and it grew out of a deep puzzle about black holes. Specifically, the Bekenstein-Hawking entropy formula, which says that the entropy of a black hole, the amount of information it contains, is proportional not to its volume, as you'd naively expect, but to its surface area, the area of its event horizon. That was deeply weird. It suggested that the maximum amount of information you can stuff into any region of space is determined by the area of the boundary, not the volume of the interior, as if the three-dimensional interior is somehow redundant, as if the real degrees of freedom, the real fundamental description, lives on the boundary. Maldaceno's correspondence gave this vague, suggestive idea a precise mathematical realization. And it gave physicists an incredibly powerful tool, because now, if you wanted to study quantum gravity, which is horrifically difficult, you could instead study the equivalent quantum field theory on the boundary, which is merely very difficult. Problems that were intractable on the gravity side sometimes became solvable on the boundary side, and vice versa. It was like discovering that a book you couldn't read in one language had an exact translation in a language you were fluent in. So here's where time travel comes back into the picture. Remember the Morris-Thorne wormhole, that traversable shortcut through space-time that requires exotic matter with negative energy density? And remember how the big question was whether the laws of physics actually permit enough negative energy in the right configuration to hold a wormhole open? Well, in 2017, Ping Gao, Daniel Jafferis, and Aaron Wall made a remarkable discovery within the ADS/CFT framework. They showed that if you take two black holes in anti-de Sitter space that are connected by a non-traversable wormhole, an Einstein-Rosen bridge, and you couple the two boundary theories together in a specific way, allowing them to exchange information through an ordinary quantum interaction, then something extraordinary happens on the gravity side. The wormhole becomes traversable. Think about what that means. On the boundary, you're just doing ordinary quantum mechanics. No gravity, no exotic matter, just quantum fields interacting. But the gravitational translation of that interaction is that negative energy appears near the wormhole throat, propping it open just enough for a signal, or in principle, an object, to pass through. The exotic matter that Morris and Thorne needed, the stuff that seemed so implausible and difficult to produce, emerges naturally from a simple quantum coupling between the two sides. Now, this is happening in anti-de Sitter space, not in our universe. Our universe has a positive cosmological constant. It's closer to de Sitter space, which has very different properties. So you can't directly apply this result to build a wormhole in your backyard. But the conceptual breakthrough is enormous. For the first time, physicists had a fully consistent quantum gravitational description of a traversable wormhole. No hand-waving about exotic matter. No classical solutions that might or might not survive quantum corrections. The boundary theory is perfectly well defined, and it says the wormhole is traversable. Period. And here's what's really interesting about this from the time travel perspective. The traversable wormhole in the Gauss-Jafferis wall construction is actually a very slow shortcut. The signal that passes through the wormhole doesn't arrive faster than a signal that goes the long way around through the boundary. It's not a shortcut in time. And this is consistent with the boundary description. On the boundary, information is just being transferred from one quantum system to another through an ordinary interaction, and there's nothing causal about that. So in this particular setup, the wormhole is traversable, but it doesn't create a time machine. Causality is preserved. But, and this is a crucial but, the question of whether you could modify the construction to create closed time-like curves to actually build a time machine within this framework is still open. Some configurations that look like they might produce time travel on the gravity side seem to correspond to inconsistent or pathological states on the boundary side. And that's exactly what you'd expect if Hawking's chronology protection conjecture is right. The laws of physics conspire to prevent time machines, and in the holographic framework, that conspiracy shows up as a breakdown or inconsistency in the boundary theory whenever you try to create causal loops in the bulk. This is a beautiful example of how the holographic approach gives you new tools to attack old problems. Instead of trying to figure out whether quantum effects destroy a time machine by doing some impossibly complicated calculation in curved space-time with quantum fields, you can ask the equivalent question on the boundary, where you have much better mathematical control. And so far, the boundary keeps saying no. No time machines. Causality is protected. But so far is doing a lot of work in that sentence. The calculations are difficult, the framework has limitations, and there are configurations that haven't been fully analyzed. The honest answer, as of right now, is that we don't have a definitive proof that time travel is impossible. We have strong evidence from multiple independent lines of reasoning, Hawking's semi-classical arguments, the holographic correspondence, various quantum gravity calculations, that nature doesn't like closed time-like curves. But we don't have a theorem. We don't have a final answer. And that brings us to something I think is really worth sitting with for a moment. The question of whether time travel is possible is not a question about engineering. It's not about whether we can build a machine powerful enough or find enough exotic matter. It's a question about the fundamental laws of physics. It's asking, what does the universe allow? What are the rules? And we don't fully know the rules yet. We don't have a complete theory of quantum gravity. We don't know whether the holographic principle applies to our actual universe. We don't know what happens at the Planck scale, where distances are so small, about 10 to the minus 35 meters, that our current theories simply stop making sense. Which means that the question of time travel is entangled, no pun intended, well, maybe a little intended, with the deepest unsolved problems in physics. And one of those problems, one that connects to time travel in ways that might surprise you, has to do with the nature of time itself. Not time travel, but time. What is it? Why does it flow in one direction? Why do we remember the past but not the future? This is the arrow of time problem, and it's been haunting physicists since the 19th century. since a bearded Austrian named Ludwig Boltzmann sat down and tried to figure out why heat always flows from hot to cold. That's what Boltzmann was wrestling with. It sounds like such a simple observation, right? You leave a cup of coffee on your nightstand and it cools down. It never spontaneously heats up. An ice cube in a glass of water melts. It never spontaneously reforms. A drop of ink in a glass of water spreads out into a uniform tint. It never gathers itself back into a neat little droplet. These things only go one way. And Boltzmann wanted to know why. Now, here's what made this such a puzzle. By the mid-1800s, physicists had figured out that heat was really just the motion of atoms and molecules. Temperature was just a measure of how fast those tiny particles were jiggling around. And the laws governing those particles, Newton's laws of motion, are perfectly reversible. If you filmed a single molecule bouncing off another molecule and played the film backward, it would look completely legitimate. Both directions obey the same equations. There's nothing in the fundamental laws of mechanics that says time has to go forward. Nothing that says hot things must cool down. Nothing that says ink must spread. The microscopic laws don't care about the direction of time. And yet the macroscopic world, the world you and I actually live in, very clearly does care. Things fall apart. They don't unfall apart. That asymmetry, that one-wayness of the everyday world, is what physicists call the arrow of time. And Boltzmann's great insight was connecting it to something called entropy. You've probably heard the word entropy before, and it's one of those terms that gets thrown around a lot, sometimes loosely. But the core idea is actually pretty intuitive once you sit with it. Entropy is, roughly speaking, a measure of how many different microscopic arrangements of particles would look the same to you from the outside. Think about it this way. Imagine you have a box divided in half by a partition, and all the gas molecules are crammed into the left side. That's a very specific, very ordered arrangement. There are relatively few ways the molecules could be arranged and still all be on the left side. Now remove the partition. The gas expands to fill the whole box. And here's the thing. There are astronomically more ways for the molecules to be spread throughout the entire box than there are ways for them all to be on one side. Just overwhelmingly, staggeringly more. So if the molecules are bouncing around randomly, they will, purely by chance, tend to end up in one of the vastly more numerous spread-out configurations. That's not because there's a law forcing them to spread out. It's just statistics. It's just probability. The disordered states outnumber the ordered states so enormously that the system essentially always moves toward disorder. That's entropy increasing. And that's Boltzmann's explanation for the arrow of time. He formalized this in the 1870s with his famous equation, the one that's actually carved on his tombstone in Vienna, S equals K log W, where S is entropy, K is what we now call Boltzmann's constant, and W is the number of microstates consistent with the macroscopic state you observe. It's a beautiful equation, and it tells you something profound. The reason time seems to have a direction, the reason the past is different from the future, the reason things decay and cool and crumble, it's not because the fundamental laws of physics are asymmetric. It's because the universe started in an extraordinarily low entropy state, a very special, very ordered initial condition. And it's been rolling downhill ever since. Think about what that means. The arrow of time, the thing that makes cause precede effect, that makes you age, that makes memory possible, that makes the word before mean something different from after. All of that traces back to the initial conditions of the universe, to the Big Bang, to the fact that roughly 13.8 billion years ago, the universe began in a state of remarkably low entropy. Why? Why was the initial state so special? Boltzmann didn't have a good answer for that, and honestly, we still don't have a fully satisfying one. Roger Penrose calls it the past hypothesis, the assumption that the early universe had extremely low gravitational entropy. And he's argued for decades that any complete theory of physics needs to explain it, not just assume it. But we're still assuming it. Now, you might be wondering what all of this has to do with time travel, and here's where it connects. And I think it connects in a way that's deeper than most people realize. If the arrow of time is not fundamental, if it's not baked into the laws of physics, but is instead a consequence of initial conditions and statistics, then in some sense, the directionality of time is emergent. It's not a basic feature of reality. It's something that arises from something else. And if the direction of time is emergent, then the question of whether you can go backward in time takes on a different flavor. You're not asking whether you can violate a fundamental law. You're asking whether you can swim against a statistical current, whether you can arrange things so that entropy locally decreases in just the right way. And while that's practically impossible for any macroscopic system, the numbers are just too absurdly large. It's not forbidden in principle by the microscopic laws. This is actually related to something called Loschmidt's paradox, named after Joseph Loschmidt, who was a colleague of Boltzmann's in Vienna. Loschmidt pointed out in 1876 that if you could somehow reverse the velocity of every single molecule in a system, flip every particle's direction of motion, then the system would retrace its steps backward. Entropy would decrease, and you'd see the ink gather back into a droplet, the coffee reheat itself, the egg unscramble. The microscopic laws allow this. It's just that you'd need to know the exact position and velocity of every single particle and reverse them all simultaneously, which is, to put it mildly, not practical. But the point stands. The laws of physics don't forbid it. And this connects to something really interesting that's been explored more recently in quantum information theory. Remember how we talked about the holographic principle and how information about the interior of a region might be encoded on its boundary? Well, there's a related idea in quantum mechanics about whether information is ever truly lost. And this gets us to the black hole information paradox, which Hawking kicked off in the 1970s and which has been one of the central puzzles in theoretical physics ever since. Here's the setup. Hawking showed in 1975 that black holes aren't perfectly black. They emit radiation, now called Hawking radiation, due to quantum effects near the event horizon. This radiation is thermal, meaning it's essentially random, carrying no information about what fell into the black hole. Over time, the black hole shrinks as it radiates, and eventually, given enough time, an almost incomprehensibly long time for a stellar mass black hole, it evaporates completely. And here's the problem. If the radiation is truly random and carries no information, then when the black hole is gone, all the information about everything that ever fell in is gone too, destroyed. But quantum mechanics says information can never be destroyed. The evolution of a quantum system is unitary. That's the technical term, meaning it's always reversible in principle. You can always, in theory, reconstruct the past from the present. If black hole evaporation destroys information, then either quantum mechanics is wrong, or our understanding of black holes is incomplete, or something else very strange is going on. This paradox raged for decades. Hawking himself initially argued that information was genuinely lost, and he made a famous bet with John Preskill and Kip Thorne about it in 1997. Hawking eventually conceded the bet in 2004 acknowledging that information is probably preserved, though the exact mechanism wasn't clear, and in recent years, a remarkable series of results. Building on the ADS/CFT correspondence we talked about, along with new ideas about quantum extremal surfaces and something called the island formula, has provided strong evidence that information does escape from black holes, encoded in subtle quantum correlations in the Hawking radiation. The details are technical, but the upshot is striking. The universe seems to be fundamentally reversible. Information is never lost. The past is, in principle, always recoverable from the present. Now sit with that for a moment, because it's a strange thing to hold alongside the arrow of time. On one hand, the microscopic laws are reversible. Information is conserved. The past is encoded in the present. On the other hand, entropy increases. Things fall apart. We age. We can't remember the future. Both of these things are true simultaneously. The arrow of time is real. We experience it every moment of our lives. But it's not fundamental. It's emergent. It arises from the statistics of large numbers of particles and from the special initial conditions of the universe. And this tension, this coexistence of reversibility at the bottom and irreversibility at the top, is one of the deepest and most beautiful puzzles in all of physics. And it matters for time travel because it reframes the whole question. If you think of time as a river flowing inexorably in one direction, then time travel means somehow swimming upstream or teleporting to a different part of the river. It feels like you're fighting the fundamental nature of reality. But if the river's flow is emergent, if it's a consequence of how things happen to be arranged rather than a fundamental law, then the question becomes subtler. It becomes about the structure of space-time, about what configurations are possible, about whether the geometry of the universe permits paths that loop back on themselves. And that's exactly what general relativity explores with closed, time-like curves. The arrow of time and the geometry of time are related but distinct questions, and keeping them separate in your mind is important. There's another angle here that I find really compelling, and it has to do with quantum mechanics and the nature of measurement. Because quantum mechanics has its own time problem, one that's different from the thermodynamic arrow, but equally puzzling. In quantum mechanics, a system exists in a superposition of states until it's measured, at which point it appears to collapse into a definite outcome. And that collapse, if it's a real physical process, is irreversible. It's the one part of quantum mechanics that isn't described by the smooth, reversible Schrödinger equation. It's abrupt. It's random. And it goes in one direction. Some physicists like Penrose have argued that this collapse is connected to gravity, and that understanding it properly requires a theory of quantum gravity. Others, like the many worlds advocates, argue that collapse isn't real, that all outcomes happen, and the appearance of collapse is just what it feels like to be inside one branch of an ever-splitting wave function. And this matters for time travel, because if you take the many worlds interpretation seriously, the way David Deutsch does, then closed timelike curves don't create paradoxes. They just create branching. The grandfather paradox dissolves because the time traveler arrives in a different branch. But if collapse is real, if there's genuinely one outcome and the wave function really does reduce, then the relationship between time travel and quantum mechanics becomes much thornier. The interpretation of quantum mechanics you adopt shapes what you think time travel would even mean. So here we are, deep into the night, and we've arrived at a place where the question of time travel has become entangled with the deepest questions in physics. The nature of entropy. the origin of the universe's special initial conditions, the black hole information paradox, the interpretation of quantum mechanics, the search for quantum gravity. These aren't separate puzzles. They're all connected, all part of the same vast web of questions about what time really is and what the universe really allows. And there's one more thread I want to pull on, one that brings us into the 21st century and into some of the most speculative but fascinating territory in modern physics. It has to do with the idea that space-time itself might not be fundamental. That space-time, the very fabric we've been talking about this whole time, the thing Einstein taught us to think of as a dynamic, curving, four-dimensional manifold, might actually be something that emerges from a deeper layer of reality, something built out of more primitive ingredients. And if that's true, then everything we've said about time travel, about closed timelike curves, about wormholes and chronology protection, all of it takes on a different character. Because you can't travel through something that isn't fundamental. Or rather, if space-time is emergent, then the question of time travel isn't really about geometry anymore. It's about whatever lies beneath geometry. So let's talk about that. Let's talk about what it might mean for space-time to be emergent, and why so many physicists in the 21st century have started to take this idea seriously. The seeds of this were planted a long time ago, actually. We talked about the holographic principle and ADS/CFT back when we were discussing wormholes, how Juan Maldacena showed in 1997 that a theory of gravity in a certain kind of curved space-time is completely equivalent to a quantum field theory living on the boundary of that space-time. A theory with gravity in the bulk equals a theory without gravity on the boundary. And the boundary theory has fewer dimensions. It's like saying that everything happening inside a room, every object, every motion, every gravitational interaction, is somehow encoded in a flat hologram painted on the walls. Now, when that correspondence was first discovered, people mostly used it as a tool. You had a hard problem in one theory. You translated it into the other theory where it might be easier. You solved it there and you translated back. Incredibly powerful. But in some sense, people were treating the two descriptions as just that. Two descriptions. Two different ways of talking about the same physics. But over the past 15 years or so, a deeper realization has been growing. What if the boundary theory is the real thing? What if the quantum field theory on the boundary is the fundamental description, and the bulk space-time, the interior with its gravity and its geometry and its dimensions, is something that emerges from the quantum entanglement structure of the boundary theory? What if space-time is built out of entanglement? This idea has a name, or at least a slogan. It comes from a 2010 paper by Mark van Ramsdonk, a physicist at the University of British Columbia. The paper was originally rejected from a journal, which is kind of wonderful in retrospect, because it went on to become one of the most influential papers in theoretical physics of the past 2 decades. Van Ramsdonk's argument was beautifully simple. He said, take the boundary theory in ADS/CFT. It describes some quantum state. Now imagine that state has 2 parts that are entangled with each other. In the bulk, this corresponds to a connected space-time, a smooth geometry linking 2 regions. But now, gradually reduce the entanglement between those 2 parts. Disentangle them. What happens in the bulk? The space-time starts to pinch off. The connection gets thinner and thinner. And when the entanglement reaches 0, when the 2 boundary regions are completely unentangled, the bulk space-time splits into 2 disconnected pieces. Think about what that means. The connectivity of space-time. The fact that you can get from here to there, that space is one continuous thing. That connectivity is a consequence of quantum entanglement in the underlying theory. No entanglement, no space-time. Entanglement is the thread that stitches space together. And this isn't just poetry. There's a precise mathematical relationship behind it, discovered by Shinsei Ryu and Tadashi Takayanagi in 2006. The Ryu-Takayanagi formula says that the entanglement entropy of a region in the boundary theory is proportional to the area of a certain minimal surface in the bulk. If you've been following along, that should remind you of something. The area of a surface being related to entropy. That's exactly the structure of black hole entropy, the Bekenstein-Hawking formula. And that's not a coincidence. It's a clue. It's telling you that the deep relationship between geometry and information that Bekenstein glimpsed in the 1970s is actually a special case of something much more general. Geometry is information. Space is entanglement. The shape of the universe is, in some sense, a way of encoding how quantum information is organized. Here's where this connects back to time travel. If space-time is emergent, if it's woven from entanglement, then the rules about what space-time geometries are allowed aren't really geometric rules at all. They're rules about quantum information. And the question of whether closed timelike curves can exist isn't a question about whether you can bend a rubber sheet into a loop. It's a question about whether the underlying quantum system can be in a state whose entanglement structure would correspond to a geometry with closed timelike curves. And there are good reasons to think the answer might be no, not because of some geometric obstruction, but because such a state would violate fundamental principles of quantum information theory, things like unitarity, things like the fact that quantum information can't be cloned. This is chronology protection, but from a completely different angle. Hawking proposed it as a conjecture. The laws of physics conspire to prevent time machines. But in the emergent space-time picture, it's not a conspiracy. It's a consequence. Closed time-like curves can't form because the quantum state that would correspond to them is simply not a valid quantum state. It would require a pattern of entanglement that quantum mechanics doesn't allow. The protection isn't enforced by some mechanism within spacetime. It's enforced by the rules of the deeper theory from which spacetime arises. Now, I want to be careful here because this is still very much frontier physics. We don't have a complete theory of emergent spacetime. We don't fully understand how time itself emerges. Most of the work so far has been about how space emerges, which is already hard enough. The emergence of time is even more puzzling, because in the boundary theory of ADS/CFT, there is still a time direction. The boundary theory evolves in time. So in some sense, time is present in both descriptions. What changes is the spatial geometry of the bulk. That's what's emergent. But the hope, the ambitious hope, is that eventually we'll understand how both space and time emerge from something more fundamental, something pre-geometric, something that doesn't have dimensions or distances or durations built in from the start. There's a research program along these lines that goes by the name of It from Qubit, a play on John Wheeler's old phrase, it from bit, the idea that physical reality is fundamentally informational. The It from Qubit program, which has involved people like Maldacena, Van Ramsdonk, Patrick Hayden, John Preskill, and many others, takes this seriously. The it, space-time, gravity, the bulk of the universe, comes from qubits, from quantum bits of information and their entanglement. And if this program succeeds, it won't just explain quantum gravity. It'll redefine what we mean by time. Let me give you one more concrete result that shows how powerful this way of thinking is. Remember the black hole information paradox? Hawking showed that black holes radiate and eventually evaporate, and the question was whether the information that fell in is truly lost. We talked about the island formula and how recent calculations suggest that information is preserved, that the entanglement entropy of the radiation follows a curve called the Page curve, first going up and then coming back down, which is exactly what you'd expect if the process is unitary, if information is conserved. Here's what's remarkable. Those island formula calculations work precisely because they use the tools of emergent spacetime. The islands, those regions inside the black hole that turn out to be encoded in the radiation, are a consequence of the Ryu-Takayanagi formula and its generalizations. The geometry of the black hole interior isn't fixed and absolute. It's determined by the entanglement structure of the quantum state. And as the black hole evaporates and the entanglement structure changes, the geometry changes too. New surfaces become dominant. The island appears, and suddenly, information that seemed trapped behind the horizon is accessible from the outside. This is space-time doing something that would be completely impossible if you thought of it as a fixed stage. The interior of the black hole is being reconstructed, reinterpreted by the quantum information on the outside. The geometry is serving the information, not the other way around. And if geometry serves information, if the shape of space-time is a consequence of how quantum information is organized rather than a pre-existing container, then time travel isn't really about bending space-time anymore. It's about whether quantum information can be organized in a pattern that looks like a closed, timelike curve from the geometric perspective. And every indication so far is that it can't. Not because we've proven it rigorously in all cases, but because every time physicists have tried to construct such a scenario using the tools of emergent spacetime, something goes wrong. The geometry breaks down, or the state turns out to be unphysical, or the chronology protection enforces itself automatically through the quantum information constraints. So in a strange way, the deeper we go into the foundations of physics, the more time travel recedes, not because it becomes obviously impossible, but because the very framework in which it was formulated starts to dissolve. You can't travel through time if time isn't a thing you travel through. You can't loop back to an earlier moment if moments aren't beads on a string, but emergent features of an entanglement pattern. And yet, there's something beautiful about the fact that the question refuses to fully close, because we don't have the final theory. We don't know the complete rules of quantum gravity. We have ADS/CFT, but we live in a universe that isn't anti-de Sitter. Our universe has a positive cosmological constant. It's expanding, and the holographic principle in de Sitter space is much less understood. There are hints. There are proposals. People like Susskind have speculated about what holography might look like in our actual universe. But nothing as clean and rigorous as the Maldacena correspondence, which means there's still room for surprises, still room for the universe to be stranger than we currently imagine. And that's actually one of the most honest things a physicist can tell you about time travel in the 21st century. We don't know enough yet to say the final word. The tools are getting sharper. The connections between gravity, quantum mechanics, information theory, and thermodynamics are getting tighter. But the picture isn't complete. And there's one more thing I want to talk about before we wind down, one more angle on all of this that I find particularly lovely, because it brings us back to something very human. It has to do with the relationship between time travel and computation, with what a computer can and can't do, and what that tells us about the fabric of reality itself. Because here's the thing. When you start thinking about time travel, not as a physics problem, but as a computation problem, something unexpected clicks into place, and it connects to ideas you already carry around in your pocket every single day. Let me set this up. Back in the 1930s, before anyone had built anything we'd recognize as a computer, a young British mathematician named Alan Turing was thinking about a very abstract question. He wanted to know, what does it mean for something to be computable? What kinds of problems can a mechanical process solve? And, more importantly, are there problems that no mechanical process can ever solve, no matter how clever you are, no matter how much time you give it? And in 1936, he published a paper that essentially invented the concept of a universal computing machine, what we now call a Turing machine. It's a beautifully simple idea. You have an infinite tape divided into cells, a head that reads and writes symbols on the tape, and a set of rules that tell the head what to do based on what it reads. That's it. And Turing showed that this absurdly simple setup can compute anything that any computer can compute. Your phone, your laptop, the most powerful supercomputer on Earth, they're all, in a deep mathematical sense, equivalent to Turing's imaginary tape machine. They can solve exactly the same class of problems. They just do it faster. But here's the part that matters for us. Turing also showed that there are problems his machine can't solve. The most famous one is the halting problem. Given a program and an input, can you determine in advance whether that program will eventually stop running or whether it will loop forever? Turing proved, rigorously, beautifully, that no general algorithm can answer this question for all possible programs. It's not that we haven't found the right algorithm yet. It's that such an algorithm is mathematically impossible. There are limits to what computation can do. Now, why am I telling you about Turing machines when we were talking about time travel? Because in the early 1990s, a physicist and computer scientist named David Deutsch, the same David Deutsch who proposed the many worlds resolution to the grandfather paradox, started asking a wild question. If closed timelike curves existed, if you really could send information back in time, what would that do to the theory of computation? Could a computer with access to a time loop solve problems that a normal Turing machine can't? And the answer, at least within Deutsch's framework, is fascinating. A computer that could exploit a closed time-like curve would be extraordinarily powerful. It could solve certain problems that are, for ordinary computers, effectively intractable, problems that would take longer than the age of the universe on any conventional machine. The technical class is called p-space, and it includes problems that go far beyond what we believe ordinary computers, or even quantum computers, can handle efficiently. A CTC-assisted computer could, in some formulations, solve the halting problem for finite cases, crack optimization problems that stump every algorithm we have, and do things that seem almost magical from the perspective of ordinary computation theory. Think about what that means for a second. If time travel to the past were possible, it wouldn't just be a curiosity for physicists and science fiction writers. It would fundamentally rewrite the laws of what can be calculated, what can be known, what can be predicted. It would shatter the Church-Turing thesis, the foundational assumption of computer science that says a Turing machine captures everything that's computable. That's not a small thing. That's an earthquake across multiple fields of human knowledge. And here's where it gets really interesting. Because this computational angle gives us yet another reason to suspect that closed timelike curves can't exist, or at least can't be exploited in the way Deutsch imagined, because the power they would grant to computation seems too great. It seems to violate something deep about the structure of reality. Scott Aaronson, a computational complexity theorist at UT Austin, has written beautifully about this. He argues that computational complexity isn't just a feature of our current technology. It's a law of nature. The universe appears to be structured so that certain problems are genuinely, fundamentally hard. Not hard because we're not clever enough, but hard because the physics of the universe won't let you shortcut them. And if that's true, if complexity is a physical law, then anything that would violate it, including exploitable CTCs, is probably forbidden. It's a lovely argument because it comes from a completely different direction than anything we talked about before. Hawking's chronology protection conjecture came from general relativity and quantum field theory. The entanglement and emergent space-time arguments came from quantum information and holography. And now here's a constraint coming from pure computation theory, from thinking about what problems the universe allows you to solve. And they all point the same way. They all whisper the same thing. You can't go back. But let me soften that a little, because the story is more nuanced than a simple no. What Aaronson and others have pointed out is that quantum mechanics already gives us computational power beyond classical physics. That's the whole promise of quantum computing. A quantum computer can solve certain problems exponentially faster than any classical computer, using superposition and entanglement. But it can't solve everything. There are still problems that appear to be hard even for quantum computers. The universe seems to hand out computational power in careful doses. Classical physics gives you one level. Quantum mechanics gives you more, but not unlimited more. There's a ceiling, and that ceiling seems to be well below what CTCs would provide. So you can think of it this way. The hierarchy of computational power maps onto the hierarchy of physical theories. Classical mechanics gives you classical computation. Quantum mechanics gives you quantum computation. And closed timelike curves would give you something beyond both. Something the universe apparently doesn't allow. It's as if the laws of physics are specifically designed to prevent you from computing your way around the hard problems of existence, which is a strange and beautiful thought to sit with, honestly. Now, I want to bring this all the way back to where we started, because we've come a long way tonight, and I think it's worth taking a breath and seeing the whole landscape from above. We began with the simplest possible question: what is time? And we traced how the answer has evolved across centuries. Aristotle thought time was a measure of change. Newton thought it was absolute, flowing uniformly for everyone and everything, like a cosmic metronome ticking away regardless of what happens in the universe. And then Einstein came along and showed that time is neither absolute nor uniform. It bends, it stretches, it depends on how fast you're moving and how deep you are in a gravitational field. Your time and my time are not the same time, and that's not philosophy, it's measured fact. GPS satellites correct for it every day. From Einstein, we followed the thread to black holes, Schwarzschild's solution, Kerr's rotating black holes with their ring singularities, and the strange theoretical possibility that you could pass through one and emerge. Somewhere else. Someone else. We met Gödel, the logician who showed that Einstein's own equations permit universes where you can travel in a closed loop through time and return to your own past. Einstein was troubled by this. He should have been. It was a crack in the foundations, and physicists have been trying to seal it, or understand it, ever since. We talked about the paradoxes, the grandfather paradox, the bootstrap paradox, the strange loops of causality that seem to arise when you allow backward time travel. and we saw three major responses. Novikov's self-consistency principle, which says the universe simply won't let you create a paradox. You can go back, but everything you do there was always part of the history. Deutsch's many worlds approach, which says you can change the past, but you end up in a different branch of reality, so there's no contradiction. And Hawking's chronology protection conjecture, which says the universe actively prevents closed time-like curves from forming in the first place. Quantum effects conspire to destroy any time machine before it can operate. We went deep into wormholes, Einstein-Rosen bridges that connect distant points in space-time but pinch off too quickly to traverse, and Morris-Thorne wormholes that could theoretically be held open with exotic matter with negative energy density. We talked about how Thorne showed that a traversable wormhole could be converted into a time machine by moving one mouth at high speed relative to the other. And we encountered the ER equals EPR conjecture, Maldacena and Suskind's breathtaking proposal that every pair of entangled particles is connected by a tiny wormhole, that the geometry of space-time and the correlations of quantum mechanics are secretly the same thing. That led us into the holographic principle and ADS/CFT, where we learned that an entire universe with gravity can be described by a quantum theory living on its boundary, like a hologram. And within that framework, Gao, Jafferis, and Wall showed that traversable wormholes are possible, but only in a way that respects causality. The boundary theory won't let you send signals faster than light or create paradoxes, and since the boundary theory is the deeper description, the bulk geometry has to obey those rules. We explored entropy and the arrow of time. Why time seems to flow in one direction, even though the fundamental laws of physics are time-symmetric. Boltzmann's insight that entropy tends to increase, Penrose's past hypothesis that the universe started in an extraordinarily low entropy state, and the deep mystery of why that was the case. We wrestled with the black hole information paradox and saw how the island formula and recent developments suggest that information is preserved, that unitarity holds, and that space-time itself may need to rearrange its geometry to make the bookkeeping work out. And then, in the most recent stretch, we arrived at the idea that space-time might be emergent, that it's not the fundamental stage on which physics plays out, but rather a structure that arises from quantum entanglement. Van Ramsdonk's insight that disentangling boundary regions literally disconnects the bulk space-time. The Ryutaka-Yanagi formula connecting entanglement entropy to geometric areas. The whole it from qubit program that's trying to build space-time from quantum information. And what all of this converges on, I think, is something simple and profound. Time travel, as a question, has been one of the most productive wrong questions in the history of physics. I say wrong, not because it's stupid. It's not, it's deeply natural. But because pursuing it has consistently led physicists to discover that the question itself is based on assumptions that turn out to be incomplete. You ask, can I travel back in time? And the universe answers by teaching you something deeper about what time actually is. Every attempt to build a time machine in theory has revealed a new constraint, a new connection, a new layer of structure. The wormhole approach taught us about energy conditions and the relationship between geometry and quantum fields. The CTC approach taught us about self-consistency and the many worlds interpretation. The chronology protection approach taught us about the back reaction of quantum fields on spacetime. The holographic approach taught us that spacetime is emergent, and the computational approach taught us that the laws of physics enforce limits on what can be calculated. Each no has been more interesting than a yes would have been. And here's the last thing I want to leave you with, and then we can let the night settle in. There's a kind of time travel that's real, that's happening right now, that we tend to overlook because it's so ordinary. You are traveling through time. Right now, at a rate of 1 second per second, in the direction of increasing entropy, carried along by whatever it is that makes the present moment feel like the present moment. And thanks to Einstein, we know that this rate is flexible. If you flew on a fast enough plane, your clock would tick slightly slower than the clocks on the ground. Astronauts on the International Space Station age a tiny bit less than people on Earth, fractions of a second over months. But it's real, it's measured, and near a black hole, the effect would be dramatic. You could, in principle, experience 1 year while centuries pass on Earth. That's genuine forward time travel. It's not science fiction. It's general relativity, confirmed by experiment, operating in your GPS right now. What we can't do, what the universe seems to carefully, elaborately, beautifully prevent, is go backward. And maybe that's not a limitation. Maybe that's a feature. Maybe the arrow of time, the irreversibility of entropy, the forward flow of experience. Maybe that's not a prison. Maybe it's the very thing that makes experience possible at all. Without the arrow of time, there's no memory, no causation, no story. There's no before and after. There's no falling asleep and waking up. There's no tonight and tomorrow. So as you lie there, and the ideas start to blur and soften, and the names, Einstein, Gödel, Hawking, Maldacena, Turing, start to feel like characters in a dream you're already half inside, let the thought be this: the universe is stranger and more beautiful than any story we could tell about it. And the fact that we can understand even a little of its structure, that a species on a small planet can figure out that space-time bends, that black holes radiate, that entanglement and geometry are secretly the same. That's the real miracle, not traveling through time, understanding it, even a little, even imperfectly, even in the dark, with your eyes closed, drifting off to sleep. And time carries you forward, gently, the way it always has, the way it always will, one quiet moment after another, into whatever comes next.